if we just wanted to find the average of the set of values 1, 3, 5, and 7, what would we do? Well, the idea of an average is we add up all of the values in the set, and then we divide by the size of the set, right? So our average in this case would be 1 plus 3 plus 5 plus 7 divided by 4, which would give us 16 over 4, which is equal to 4. So let's draw a picture to help us visualize exactly what we would be talking about. So if we had a graph, and we have something that looks like this: 1, 2, 3, 4, 5, 6, 7, 8. If we wanted to find the average of this set, we could visualize it as some blocks that look like this. So 1, 3, 5, and then another one at 7. Where as long as the width of each of these blocks was exactly 1, and the output was the height, this block would represent the number 1, 3, 5, and 7. And then, if we took the length, or the entire length of that interval, well, what would be the entire length? Would be 1 plus 1 plus 1 plus 1 is 4, right? So then the average in this picture would be the area divided by the length of that interval, right? So if we found the area of each of those blocks, or the area of that entire region, and then divided by the length, that would give us the average of that set of values. Well, in terms of a picture, what would that represent? Well, we got that our average value was 4. Well, what that would represent is it would be geometrically the average, if we multiply both sides of that equation by length, the average times the length has to equal the total area. So if that's the case, if this is the length, and we drew a red rectangle with the average, then this would be the height, right? In terms of our area formula for a rectangle. So the average value, or so this suggests, is the height of a rectangle with the same length that would have equal area to whatever figure we're talking about. So we did it this case with some discrete rectangles where that's very easy to visualize, because imagine I chop the top off this and place it here, and then I chop the top off this and place it here. If I did that, indeed I would construct that rectangle, right? But we want to generalize this idea from nice rectangular pieces to things that are a little more curvy, right? But this is going to be the basic idea, and we're going to build that up using the idea of Riemann sums to come up with our average value for a function. All right. So then our question is, how can we generalize this to work with functions? So let's start with this graph and see what we get. So example 2, the temperature yesterday, I wish, not in Yuma. The temperature yesterday was given by capital T of t is 20 sine times pi times t over 12 plus 50. So on this graph, it looks like our temperature is fluctuating between 30 degrees and 70 degrees. And we want to find the average of this entire thing. So if we wanted to approximate this using a Riemann sum, well, let's start by making some approximating rectangles. Using the right endpoint, I would create some rectangles that looked like this, right? Well, at first glance, then our average in red, well, what would be the width of each of these rectangles right here? Well, from 0 to 6, 6 to 12, 12 to 18, and 18 to 24, each of these would be 6. So that's going to be our delta x in this case, would be 6. And then we want to come up with our average, right? So our average is going to be, well, if we think, what's our formula for delta x? Delta x is b minus a divided by n. So in our case, our b is 24, our a is 0, and how many rectangles are we using? 4, which indeed gives us 6, right? So then, we can use this idea to help us out. Well, the idea would be, regardless of what we're going to have here, we would need to add up all of those areas. So to give us an approximation of these rectangles, we would have something like f of 6 plus f of 12 plus f of 18 plus f of 24, right? In terms of our picture, that just gives us a height, right? So we're not quite where we would need to be yet. So then we would need then to multiply each of these by the delta x, right? And our delta x would be 6, so times all of these by delta x. And then we would have to divide everything by the entire length of our interval, which was 24, right? So in terms of this, what would happen is we would have those reduce out, and we would get 4. Well, where have we seen the number 4 before? Well, this happens to be our number n in this case, right? So this strongly suggests then that our average in general is going to be the following. The average would be equal to the sum as I goes from 1 to n of f sub xi divided by n. And if we take the limit as the number of approximating rectangles goes to infinity, so the limit as n goes to infinity of the sum as I goes from 1 to n of f of x sub I over n, we want to realize this in terms of an integral. But we don't quite have that here. So that's where our delta x is going to come in handy. So using our formula for delta x, we have delta x is equal to b minus a over n. Solving for n, we would get n is then equal to b minus a over delta x. If we substitute this into our equation here, we get the following. The limit as n goes to infinity of the sum as I goes from 1 to n, and I'm going to write it out this way, f sub x sub I all over b minus a all over delta x. Turn the numerator into a fraction by putting it over 1. So if we have a fraction divided by a fraction, we multiply by the reciprocal. And that leaves us with f sub xi over 1 times delta x divided by b minus a. So now our limiting value, our sum depends on I, and our limit depends on n. So this piece right here, this is constant with respect to both the sum and the limit. So we pull that out in front of everything. So we have 1 over b minus a of the limit as n goes to infinity of the sum as I goes from 1 to n of f sub xi times delta x. This is exactly the definition of the integral of the function from a to b. So solving, we get that our average is equal to 1 over b minus a times the integral from a to b of f of x dx. So the average value of a function is 1 over the length of the interval multiplied by the integral of the function over that same interval. And that in general gives us our formula for calculating the average value. So now after deriving that formula, let's go ahead and answer our question. So if we do the integral from 0 to 24 of our function, and we're going to have 24 minus 0, and our function is equal to 20 times the sine of pi times t over 20 plus 50. And we do that dt. So we need to evaluate our integral. So 1 over 24. And the antiderivative of sine is going to be negative cosine of pi t over 20. And then we need to divide that by the derivative of the inside, so pi over 20. We can also use u equals pi t divided by 20 if that is your desire, and you will get the same thing. Plus the antiderivative of 50 is 50t. And then we evaluate that from 0 to 24. Well, that thing's a bit of a mess, so I'm going to just put all that into my calculator under y equals. So to clear that out, I'm going to have 1 over 24 times 20, so I'll just do that as 20 over 24. And then parentheses, oops, not there, pop up. I'm going to have another fraction, and I have negative cosine of pi times t, or x in this case, over 20, all over pi over 20. And then plus 50x. So I get all that put in, and then I just go alpha trace, and I'm going to go y of 24, and I am going to take away y1 of 0, hit enter, and that is not the correct number. So what did I type into my calculator wrong? Yeah, because I wrote the problem down wrong. So, sorry guys. When I transcribed the problem, I wrote it down wrong. It's supposed to be 12, not 20 in the bottom. That's why when I was looking at my notes, I'm like, the answers don't match. So, when I wrote it down, that was supposed to be a 12. So let's go ahead and correct each of those. Oh, I gotta fix those in my calculator. All of those should have been not 20s, but 12s. 12, and in the denominator, I should also have a 12. Alright, so now when we do this, should have gotten this. And, sorry, one more thing. That 1 over 24 should have been multiplied to both of them on our calculator. That one's a little hard to put into our calculator. So this also needed to be divided by 24. And that should fix our problem, because the 1 over 24 here was outside the integral, so it belonged to everything in there. So now, we get the value we're supposed to, which is 50. And let's go back to our graph and see why that's the case. So we get the value of exactly 50, which happens to be this value right here. Well, the reason for that is the area here above that curve is exactly equal to the area here that's below it. So these are equal but opposite. So in this case, that's why we got exactly 50 for our average temperature that ranged between 70 and 30 degrees in that picture. All right, so formally, here's our formula again. F average, which is represented by F with the subscript AVE for average, is given by one over b minus a, the integral from a to b of f of x dx. So find the average value of x squared on the interval 0, 2, and what does it represent? So our f average is going to be 1 over 2 minus 0 times the integral from 0 to 2 of x squared dx. So that gives us 1/2 times the antiderivative of x squared is x cubed over 3, and we evaluate it from 0 to 2. So that's going to be 2 times 3 is 1/6, and we're going to have 2 cubed minus 0 cubed, giving us 1/6 times 2 cubed is 8. So 8/6, or if you use your calculator, you can get the same thing, 4/3. So once again, if you want to just put it in your calculator, you would have 1/2 times x cubed over 3 is going to go alpha trace y of 2, take away alpha trace y of 0. And we get the same value, 4/3. And so geometrically, what is it that the 4/3 represents? Well, we have 1, 2, 3, so here would be 2, and 4/3 would be a third of the way here. So 4/3 would be the height of a rectangle that would have the same area as that part that is shaded in blue. So in this, the area of the rectangle is equal to the area under the parabola on the interval 0, 2. So geometrically, the average would be the height of the rectangle that would have the same area as the area underneath that curve. All right, so to find the average value of this function, it's going to be 1 over b minus a, so our b is e to the 7th minus e times the integral from e to e to the 7th of the natural logarithm of x over x dx. So we need to find our antiderivative, and to do this, we're going to need to make a u substitution. So we let u equal the natural logarithm of x, then our derivative du is 1 over x dx, or solving for dx, we get dx is equal to x du. So we substitute into our integral, and we're also going to need to change our limits of integration. So we have e to the 7th minus e, and then our integral, it's going to be the natural logarithm. We replace the x with our lower limit of integration, the natural logarithm of e, and our upper limit of integration becomes e to the 7th. And then we substitute our ln x becomes a u all over x, and our dx becomes x du. Our x's reduce out, and we can reduce some of the other parts as well. So we get 1 over e to the 7th minus e. The natural log of e is equal to 1, and the natural log of e to the 7th is 7. And we're left with u du. So then our antiderivative of u is going to be u squared over 2. When we evaluate that from 1 to 7, so we get, putting all of our constants together, 2 times e to the 7th minus e times 7 squared minus 1 squared. So 7 squared is 49, 1 squared is 1. So we get 48 all over 2 e to the 7th minus e. 2 goes into 48 24 times, and we get 24 over e to the 7th minus. And that would be our average value of our function on that appropriate interval. All right, so let's kind of recap. So if we didn't know how to directly do an antiderivative, really right now the only tool we have in our toolbox is a u substitution. And the way we pick u is we look for a function u whose derivative is also present in the problem. Since the derivative of the natural logarithm is 1 over x, we noticed that we did have the 1 over x here. So that gave us the clue that we'd picked the right value. And then after making our u substitution, we changed our limits of integration, and then we had a nice integral, the integral from 1 to 7 of u du, which made our life a lot easier when we were calculating that integral. All right, so let's take a look at our next example. Well, it's not quite an example yet. So let's talk about the mean value theorem for integrals. But before we talk about the mean value theorem for integrals, let's just talk about the mean value theorem. So the mean value theorem says the following, and this is from last semester. If f is differentiable on the interval AB and continuous on the closed interval AB, then there exists a number C such that f prime of C times b minus a is equal to f of b minus f of a. So that's our mean value theorem for derivatives that we talked about last semester. And geometrically, what was it that the mean value theorem said? Well, in terms of a picture, imagine we have a curve that looks like this. So here's our curve f. And if we have our points A and B, what this says geometrically is if we were to create the secant line through the points A, f of A, and B, f of B, it claims then there exists a number C somewhere in AB. I left that part out. Sorry. C in the interval AB such that. So there's a number c in between the numbers a and b, where if you go up to the curve and you find the tangent line at that point, at this point, the tangent line I'll do it down here. The tangent line is parallel to the secant line. And the mean value theorem guarantees that if our function is differentiable on the open interval and continuous on the closed interval, it guarantees that there exists at least one number c where that happens, where the slope of the tangent line is equal to the slope of the secant line. Said another way, the slope of that secant line on AB is the average rate of change of the function f on the interval AB. So it says that at least one point, the instantaneous rate of change is equal to the average rate of change. So we want to generalize this to integrals. So let's apply this to capital f of x, which is equal to the integral from a to x of f of t dt. So if we have a function now that is defined in terms of an integral, we want to apply the mean value theorem. So the mean value theorem using capital F, so the first thing we need to do is calculate, well, what is f prime? So using the fundamental theorem of calculus, part 1, what is the derivative of capital F of x? So f prime of x is going to be equal to, well, when the upper limit of integration is just an x, we're going to get f prime of x is equal to little f, where little f is the integrand of the function. So our mean value theorem would then be f prime evaluated at c, sorry, I'm using b and a and something else, so let's make this a little d as to not confuse anything. So we have then f prime of c times b minus a is equal to, and then according to this, f of b minus f of a, which is going to be f of b minus f of a. That's the reason I had to change this, is I'm using a somewhere else. We don't want to use the same thing twice. So then f prime of c, then according to our derivative, this is going to be from this part right here. F prime of c is going to give us f evaluated at c times b minus a is equal to f of b. Well, that's going to be the integral from d to b of f of t dt minus f of a, which is going to be the integral from d to a of f of t dt. So now we want to simplify this expression, right? If you don't remember exactly what your properties of, from your properties of integrals, what this is, let's draw a picture. So whatever our function f is, we're going to say it looks like this. For no reason whatsoever. There's f, and then we have some numbers. We have the number d, we have the number a, and we have the number b. So the integral from d to b of f of t, well, in terms of this picture, it would be this area underneath the curve, right? And if we were to look at this integral, the integral from d to a, well, that would be this area, right? So if I were to subtract the the orange integral from the blue integral, what's going to happen? Well, right here, I would be adding this part and then subtracting it, so this would reduce to 0, right? And what would be the only thing that would be left? So then this area right here is the integral from a to b of f of t dt, right? Because we subtracted off those two bottom intervals. So that's what we're going to get here. So putting all of this together, we get f of c times b minus a is equal to the integral from a to b of f of t dt. All right. So this is true for any numbers. So finally, let's just let we're good. Let's just paste our picture. We get this, which is going to be the mean value theorem for integrals. So the mean value theorem for integrals is actually just the mean value theorem, but all we did was use a function that was defined in terms of an integral. So here's our formal statement. As we saw, there's our mean value theorem. And then our mean value theorem for integrals is this, which we got just above, right? So we have our mean value theorem for integrals, but if we were to divide both sides of that equation by b minus a, f of c times b minus a equals the integral from a to b of f of x dx by b minus a, we end up with the following. F of c is equal to 1 over b minus a times the integral from a to b of f of x dx. And what is this piece right here? By definition. That is exactly the definition of f average. Right? So this piece in the mean value theorem for integrals is f average. So combining those two ideas, going back to our geometry, what does the mean value theorem for integrals tell us geometrically? So what does this tell us geometrically? So remember, the mean value theorem for derivatives said there existed a number in between a and b where the slopes were equal. Well, coming back to our picture, this picture from example 2 hints at what we're talking about. So the c is this. It says there exists an input in the domain such that the height, or f average, there exists an input where the function is equal to the average value, right? So basically what it's telling us is that the mean value theorem for integrals guarantees that there's at least one input, x, that when you put it into the function, the output f of x is the height of the average rectangle that would give you the same area. So the c is the input where f of c is the average value of the function. So the mean value theorem for integrals guarantees there exists an input where the function height is the same as the average value. All right, so let's put all of that together to work on example number 4. So find the value of c for f of x equals sine x on 0 to pi such that f average is equal to f of c. So in order to do this, what do we need to find? F average, right? So in order to use this formula, we need to know what f average is, and then we're going to set f average equal to the function and solve for the corresponding x value. So the first thing we need to do is find f average. So we know f average is 1 over b minus a times the integral from a to b of f of x dx. So we get 1 over pi times the integral, and what is the antiderivative of sine? Yeah, we get negative cosine, and then we evaluate that from 0 to pi. So we get 1 over pi times the negative cosine of pi minus the negative cosine of pi evaluated at 0. So we get 1 over pi times negative, and the cosine of pi is negative 1, minus the cosine of 0 is, so this minus is this minus, just to be clear. So then inside I have this minus, and what's the cosine of 0? 1. So we get 1 over pi, and minus, 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 minus. All those turn into pluses, and 1 plus 1 is 2, so we get 2 over pi. So that's our f average. So now step 2, we need to solve f average equals f of x for x. So we need to solve the equation 2 over pi is equal to our f of x, and our f of x in this case was sine x. So to solve this, we take the inverse sine of both sides. And the inverse sine and the sine reduce out. That's the whole reason we did that. The inverse sine of 2 over pi doesn't really reduce nicely. I mean, you can turn it into an ugly decimal. Not recommended. And we get our value for x. So this is the c or the height that gives the same area underneath the curve. So in terms of our picture, let's go ahead and graph our sine function. So if we were to graph sine x. And then we're also going to graph 2 divided by pi. And let's go ahead and change our window. So let's make our x min 0, and we went to pi, so let's make our x max pi. And let's go ahead and scale our x-axis and point 5s. Let's make our y min equal to -1, our y max 1. Let's do our y scale as 0.1. So we get that, and we get this. So in terms of our picture, we found our points here. So if this is 2 over pi, we have the area of that rectangle, and we also have the area underneath the curve from 0 to pi of sine x dx, which would be this area. And those two areas are equal, right? And we found the c value, which is here, so that is the inverse sine of 2 over pi. Turns out there is another one right here, so this one's not 2 over pi, but by the symmetry, that is pi minus 180 degrees. So 180 degrees minus the sine of 2 over pi. So let's just verify that we actually got the correct answer. So if we wanted to use our calculator to actually find that point, we would go second trace, choose calculate, choose intersect. So first curve, second curve, and then guess. Let's get close. We hit enter. So it gives us our number 0.69. This, and if we go 2 divided by pi, we get, oh, sorry, not 2. We need the inverse sine of 2 divided by pi. My bad. Let's type the right number in. And there we go. We get the same value as we should, right? Because we found the value where that happens, the input that has the output that we are looking for. And that output was 2 over pi, not the input. All right. So that is what our mean value theorem for integrals represents.